And so blockchain cryptographically guarantees that a history of events hasn't been tampered with. This allows all the interested parties to have a shared history. So I showed you guys the quotes from Sapiens yesterday, and I kind of argued at a philosophical level that what we're really trying to do here as humans, all the way from the printing press through the internet and now to blockchain, is come up with a shared history together. And I'm going to get technical about how we do that using the cryptographic tools that you guys learned in week 1. And so one thing that's cool about the blockchain is that it not only allows us to like have cryptographic guarantees that we have a common understanding of history, it actually allows us to do that in O of 1 time. So you might consider that I give you like 2 books and I ask you, hey, please read these books and tell me if they're the same. And that would typically be like an O of N process, right? You'd have to read both books in their entirety and compare them, and the bigger the books are, the longer it would take. But with blockchain, that's not actually the case for some reasons that we'll see shortly. With blockchain, you can look just at the tip of the chain, the most recent block, or in the analogy, you can look just at the last page. And if just the last page is identical, for some reasons that we'll see with a blockchain, you can actually know that the entire story is identical and hasn't been tampered with. So if you meet some new random friend and you want to make sure you're on the same sort of chain as them, you just compare your last blocks. You don't have to go all the way back through your history until you find out that every single block was the same. And that's one of the beautiful things of the blockchain data structure. So here's how it looks. It's a hash-linked list. So you might have encountered like a linked list data structure in a regular old programming course. And so I've drawn each block here, and each block has a little piece of payload. You can think of this as like one part of the story. And so the example story I'm telling here is like, it starts somewhere else. I'm not starting all the way back at the beginning. I'm starting in the middle. It says like, hey, then Alice jumped. Okay, what could come next? Any number of things could come next. So we wait for the next block, and we get the next piece of the story. The next part is out the window. Oh my, that sounds scary. Well, what happened next? Who wants to say what happened next after she jumped out the window? Can you see it up there? Anyone have a mic? Or a hand? Okay, yeah, go ahead. Okay, yeah, that's what one of them says here, right? And she broke her leg. So that's a perfectly valid story that could come next. But there's this interesting thing up here, which is that she found out that she could fly like Icarus. So what I'm trying to show with this slide is that a blockchain, even though we usually call it a chain and we usually focus on a linear piece of it, it's actually more of a tree-like data structure. And you can have these forks at any point. You know, we could imagine that we had another piece of story coming off here. Then Alice jumped into the swimming pool, right? There's a lot of different ways you can do it. And what we'll see later is that we're going to take all of these different potential stories and are deciding which one is the real one. Was there? Okay, throw the mic right back to this guy. Who has a mic up here? Good throw. Put your hand up if you want it. He doesn't know where to throw. All right, what's up?
Why are the arrows pointed to the left versus the right?
Yeah, great. Okay, great question. So these things are called parent pointers. So if you think of a typical linked list like you would have in memory and computer science, it's usually that you like start with the first element and then the arrow points this way. It's like the memory address where you'll find the next block. So I'd say a blockchain is different in 2 ways. One is what you said, the arrows point back the other way. And the other thing that's different about a blockchain is that it isn't a memory location. The arrow doesn't represent a memory location or something that you could mutate like that. It actually represents the hash of the previous block. So I use this little like hash brown potato icon to represent hashes. So if you imagine taking like this entire block, whatever data structure that is, you can think of it as like a Rust struct or a JSON object or something like that, and you jam it through your favorite hash function, you get some data here. And I'm still on your question, don't worry, I didn't forget. The reason they point backward is because what we do with that hash is that we take that hash and we put it into the next block. So when I create this block that says out the window, it's important that people know where in the story I'm trying to insert that, right? I wouldn't want out the window, wait, let me come up with a better example. Imagine I author this block. I wouldn't want Anne broke her legs to come here after this block. That wouldn't make sense because it would say Alice jumped out the window and found that she and broke her legs, right? That's not even a sentence. And so the reason that we have the arrows pointing backwards is so that we can always know where exactly in the chain are we adding this new data. Okay, good question. Any other questions or comments so far? Okay, so here's the term Genesis block. This one basically just introduces the notion. We call it Genesis block at the very beginning. The name comes from like the book of Genesis, like in the Jewish mythology. And I really, really love that term because it kind of reinforces the point I was making with the Sapiens book up here. You know, we're really, this is all about our shared story in the same way that like all of the traditional like religious organizations have their text and their history, and they reinterpret it and build their worldview today based on it. That will be what we have here. You know, we have some old blockchain and we'll have a complete history of a system, and based on a shared understanding of that system, that's what allows us to like coordinate today. So that's our goal there, and it's called the Genesis block. And then there is also the technical detail, which is that like the Genesis block is a block just like every other block, and so it has all the same fields, including parent. And so we have to put something in the parent field, even for the Genesis block. Okay. So the convention, the most common convention is just to put 0 there. And I'll make the subtle point that it doesn't actually have to be 0. The important thing is that the people who are using this blockchain all pick some value and agree on it. So maybe like we wanted to put 0x123456789 A B C D E F. Maybe that's our like magic hash that we want to use as Genesis. That's great, you totally can, but the most important way to do it, or most common way to do it is like this. And the reason that I'm kind of drilling in on this arbitrary choice is because you can consider a world, maybe 100 or 1,000 years from now, where our blockchains are very, very long, and new people are born and want to use them and don't want to sync their full nodes. And what they may do many years from now is say, okay, forget all of that old history, or maybe don't forget it entirely, but I don't need to sync it all myself or recheck it all myself. Instead, I'll treat this block as the Genesis block, which one that I'm seeing recently. Maybe it's like the block in which my birth certificate was noted or something like that. So that's why I'm digging in there. Was there, yeah, go ahead.
Sorry, if you could just go back to the previous.
Yeah. This one? Oh no, that's not the right one, is it? That one.
I'm just in terms of the second, where the 2 hash browns are on top of each other.
This one? Or here, these?
Sorry, the 2 lots of hash.
These guys? Yeah.
Yeah. So you've still got the same hash number for both of them.
Yeah.
And then they go in, but then the hash browns have above them in purple have different.
Yeah, right, exactly. So what the hash brown potatoes and these numbers, this represents like the hash of this block right here. And similarly, these are the hash of this block right here. And similarly, hash of this block right here. Now, the parent here, this is actually a data field inside of this thing. So let's say I wanted to make a new block that goes like right here and extends this broker leg story. What I would do, I like draw my pink square, and then I'll put my parent field, and I have to take this one that already exists. That's how we know that my story is going to continue this story. So we take this hash, put it in the parent field, and then I make up whatever words I want.
Okay, and when you say that I want to make a new block, I couldn't make a new block as a non-developer. Is it only the developers who decide what these blocks look like, or how do you determine when you need more blocks?
It's not developers, it's actually people who are running the software. And when you need more and who gets to author them is what Andrew's going to talk about later on today. Yeah. But it's not developers, it's like, Bitcoin miners, for example, or like Ethereum validators. Great question. Was there one over here? No, okay. Okay, hey, state machines. This should look familiar, right? We talked about this a lot yesterday. So for a state machine, we've got our states, 2 in this case, or this is a history of 1, right? So it could go on forever and ever and ever. And then in order to switch between those states, we make these transitions. So hopefully that's pretty familiar since we were building those yesterday. Whoops. So now we're going to glue them together. This is maybe the most important slide on the deck. So I think this is your minimal viable blockchain solution. It isn't that practical in terms of like performance or real world use, but this is the core idea right here. And the way that it works is that you start out with a Genesis block, just like always, and instead of adding pieces of story that are like English words or English sentences to be interpreted by a human, what we add is state machine transitions. And so you think of some Genesis state that you start your blockchain with, and then what the blockchain does is it tells you this transition happened, and then this transition happened, and then another transition happened. And so once we've agreed on the genesis state, and once we have a blockchain to tell us the entire story of its history, all of the transitions, we should all be able to agree on the current state. So yeah, this is actually probably a better way to show it. So with our genesis block, there's some state that we start with, okay? Let's say we're about to launch a new blockchain. We publish these two pieces of data. And from here, other people start adding blocks onto the chain. So we have this one here. And basically what it says is like, there's some state transition we want to make. And so what we do is we take our state machine, we call the next state function that you guys were writing yesterday. We pass in the transition. Maybe it says flip the second switch. And then we get out some post state. And maybe it says both lights are off. Then we get another transition. Maybe it's turn the first switch on, and then we get out some next state. Maybe it's first one's on, second one's off, etc. And so this is the way that we use the blockchain to track not some arbitrary history, but a history of a specific technical, precise thing called a state machine. And remember, we've got the cryptographic pointers here as well.
Question.
Who's speaking?
Me.
Okay, go ahead.
So the blockchain exists like with the transitions basically.
Yeah.
And the state is computed basically by the state machine.
Yep.
When requested, right? My question.
Say it one more time. Sorry, say it one more time.
So we have the blockchain just
Yep.
Holding transitions.
Yes, yes.
I assume also the genesis block would also, like, are you saying there's two separate chains here, basically?
Okay. So this one, I would not call this one a chain. It's certainly not a blockchain. I mean, I get it kind of looks chain-like in the sense that they're linked, but I would say in this class, we should reserve chain to mean blockchain, and this one is a blockchain.
Yeah.
This one is not a blockchain. This is just a history of states.
Okay, but the history of states, like, there's a genesis state.
Yeah, yep, exactly. The genesis state corresponds with the genesis block, and state 1 corresponds with block 1.
So, but the genesis, can we derive the genesis state, just from the genesis block?
Now, that's a great question, and the answer depends on what blockchain you're using. So with Bitcoin, you can, because in Bitcoin, the genesis block has everything you need. It's basically just like the original issuance. That's it. In other cases, no. So like most substrate chains or chains in the Polkadot network, no, you can't, because they have like some rich genesis state with initial allocations and a million other things. Who are the initial council members and whatever.
So actually, what is more primal is the genesis state, not the genesis block. Like you could
Define primal.
Well, you could derive the state from the genesis state. You can derive the genesis state from the genesis state. You can't derive anything from the genesis block.
Well, I wouldn't say you can derive the genesis state from the genesis state. It just is, yeah. If your goal is to get the genesis state, then yes, it's better to ask for it directly than to ask for the block and hope that you can derive from it.
Yeah. And then my
Yeah.
second question is
Yeah.
like, basically, if the state isn't stored,
Yeah.
the blockchains, the blocks in the chain are stored.
Yeah.
But like the state needs to be inferred from like traversing the blockchain.
Yeah.
With the state machine.
Yes, bingo. So maybe what you're observing is the key thing, that the states do not live in the blocks. Yep, that is absolutely right. The blockchain state doesn't live in the blocks, not in the blocks. Question for you, where does the blockchain state live? Not in the blocks. Everybody say it. Where does the state live? Bingo. Okay, yeah, that's a good one. That's a good one in a comment.
Try again if you want.
Yeah, we'll take a couple more tries.
But yeah, regarding like computation time, like that's my question. Like, what is the computational time?
Yeah, okay, so what is the computational time depends entirely on what is the state machine and what is the transition, right? So at this point, I'm just saying we have some state machine, we're executing some transition. If this is like there's one light bulb and one light switch, and this says flip it, the computational time is however long it takes to do a Boolean operation on your CPU. If this is like some rich DeFi thing and you're doing some degen stuff that has like 10 internal transactions, the compute time will be much longer.
But I mean more like, do we need to like go back from the genesis every time we want to derive?
No,
the
no,
state?
no,
Or
no,
when
no.
you
So
look
the way
at
you
it-
typically do this is like if you're a person who cares about the blockchain, you know the history of the blockchain because you're watching. You know, you're sitting there listening to the network as new blocks are coming in, and every time you hear of one, you know, okay, pretend this is me. I know about 2 blocks, and therefore I know about 2 states. And then all of a sudden, someone calls me up across the internet and says, "Hey, here's a new block." So what I do is, I mean, first of all, I add this block to my database. That's pretty straightforward. And then what I do is I look up the old state out of the parent state out of my database, and I look up the transition that's in the block, and I run my state machine. Might take a long time, might not. And what I get is state 2,
Okay.
and I put it in my
you store it,
database
so
over here.
basically you store it. As
Yeah, I store it on my own local disk on my node, not in the blockchain data structure or anything like that. Great questions. Yeah, go ahead.
So the states are living outside of the blockchain on your like machine or whatever. But then why is that like so then the next time that a block is created, does that mean that it's taking data from your state machine, like the other person peer to peer whatever is taking data from your state machine and then it's also taking data from the blockchain to create?
So don't think of it as your state machine. It's some state machine that like we, the users of the blockchain, value. So like, for example, if you're a Bitcoin user, then the state machine is their rules about like, you can't spend more money than you have and stuff. So it isn't really yours or mine. It's like our state machine or like the state machine. That we all agree on what it is. And so because we all agree on what the state machine is and because we all agree on the history, that means that we all agree on these states. So like, I was telling him like, I'm gonna compute state 2 myself on my computer privately. I'm not gonna tell you the answer or anyone else. But you're all gonna make that same computation. You all have this, you get it out of your database. You know it's the same as mine because we have the blockchain tracking it. And then you run this compute yourself and you get this state here. Does that answer your question?
It does. So where do the states live?
Where do the states
Yeah,
live?
sorry,
Yeah,
sorry.
they
On
live
your-
like
on
on my
your-
hard disk
on your
right
chart.
there,
Okay,
and
got it.
also on your hard disk and on her hard disk, on on everybody. This is why it's a replicated state machine, right? The states are replicated
So
on
wait,
all of
then
our systems.
where's the blockchain?
So the blockchains also live on our disk, but in a different part, right? The point is that in some sense, you can think of the blockchain as this abstract thing that just is, but I mean, really, we're all storing it on our disks if we're running nodes. Yep. So they both live on your disks, but not like in the same files. And the important point of this slide is that these state boxes are outside of the block boxes. They're not in there. So when I like call you up over the internet and I'm like, hey, I found a new block, you should add it. I'm not telling you the state. I'm only telling you the story. It's up to you to figure out what's happening in the universe now, like what the balances are, or whether the lights are on or whatever, whether the clothes are clean.
And that enables, because everyone's getting the same answers, that enables everyone to kind of go, okay, this is correct. It's not
Bingo.
incorrect.
Yep.
Okay.
Yeah, exactly. Oh, yeah, exactly. Yeah, so I want to come back to you too in a few slides because you're already getting at something really important that's coming up. In fact, look at this. So let's talk about state roots. So we can hash anything, right? A hash function takes in arbitrary data and gives you out a fixed length hash. We already saw earlier that we can hash the blocks and we already have a use for those hashes. Now, let's start hashing our states as well. So I can take this state, jam it through my favorite hash function, I get some value. And what I do now is I cryptographically anchor the block to the state that's associated with it. So let's keep talking through this example that we were doing earlier. When some new block comes in, and I look up the old state, I execute the next transition, I get the new state. What I need to do now is hash my new state. Remember, this state 2 here, I just calculated it all by myself on my computer. No one in the world even knows I did it. And what I do is I hash it, and I get some hash. Let's say it's like, well, I shouldn't have used the same value. That was actually like pretty much the only value I shouldn't have used. So sorry about that little typo. Let's pretend it says like 1, 2, 3, 4. I make sure that when I hash my state, it's the same state as what was in the block that came to me, the same state hash. And that's how I know that this block is valid. So maybe that'll make more sense if I talk through the scenario of an attacker. Imagine I'm some like bad guy, some bad blockchain user, and I want to modify the story in some selfish way. Maybe I want to get myself more coins, or maybe I really want the lights to be off, or the clothes to be dirty, or whatever in your favorite state machine example. And so I construct a block like this, with a goofy state root here, okay? And I send it around and I try to get you guys all to put it in your chain and think it's real. Here's what you're gonna do and here's why I'm not gonna be able to trick you. You're going to look up the old state. You're going to execute this transition. You're going to get some new state, the correct one, the real one, not the one that I'm trying to trick you into. And you're going to look at the hash that you get, and then you're going to compare it to my hash. And you're going to be like, hey, wait a second here. The state that I got is not the state that this block says it's supposed to be. So this block, something's wrong. I know something's wrong because I checked myself. And therefore, I can throw that block away because it's not valid. It didn't execute the state machine correctly.
One question.
Yeah, go ahead. And then throw the mic behind you when you're done.
The hashes seem to be like, so the parent in the second one is referring to some
Yeah, okay. There is one tiny typo, so let me point out exactly where it is. This is good here. The Genesis block links to the Genesis state. That's great. And then block 1 links to state 1. That's great. The only thing that's a little mistake is that I think I just, when I was making my figure, I like copy pasted and I accidentally used the same hash. That's what's wrong.
But in the second block, the parent, where is this coming from? Not
It's not shown on here, but it's the hash of the Genesis block. Let me go back to that one. This is how we get the parent hash. It came from here. You know what I mean? I hash this block, and then it goes into this one.
Okay. So then if you go back to...
sorry, wait, I'm going the wrong way. This one?
Yeah, so then the Genesis state, so the parent in the second block, shouldn't that be the hash? Okay, the value of parent in the second block.
Yeah, you're talking about this value right here, right? Yeah.
Shouldn't that be the Genesis state
It should
hash?
not be this. No, absolutely not. These are not state hashes. These are block hashes.
Okay.
We're not this. In fact, that's what this arrow is indicating.
Okay, so
this parent hash is the hash of this
you're
block.
just not displaying the hashes of the...
Yeah,
hashes of the whole
these
block.
hashes down here, these are state roots. They go in this field. They never go in this field. Good question. And the guy 2 rows back had a question too. And then you can be next, JP. And then that might be it. Oh, there's so many. All right, let's make them good. Ask yourself, is this a good question?
Yeah, this checking of the correct block to insert in the chain,
Yep.
checking if you are misleading,
Yep.
is this happen on the mempool, right?
No. So we haven't talked about mempool at all. I will at the end of this lesson, but we're not to that yet. This is all in the blockchain data structure. We're talking about on-chain stuff right now.
Yeah. I might be getting ahead, but I know blockchain for like at least Bitcoin, it's already up to like, I don't know, like 500 gigabytes. My question is, what's the necessity to still store it all together? And,
Yeah.
I mean, you could be able to like verify, I'm pretty sure, but how are we protected from like these original like 500 gigabytes to be like
This is a good
safe?
question, but I want you to ask it to me again on my forks slide. Can you remember it and ask me then?
Okay.
Okay, thanks. Do you want to go? All right, chuck it back there.
If,
You can do it, man. Let's get athletic. This is athletic camp, right? Or is this nerd camp?
Hello, for the Genesis state, you have one data, right? And for the transition blocks also, you have another data.
Okay.
So there are 2 of them.
Yep.
So my question is, if you only get the Genesis state or the state data, can you rebuild the transition?
In general, no. It might be the case that if your state machine is simple enough, you can. Like if I tell you that here the light bulb is on and here it's off, like that state machine is simple enough that you know there's only one way you could have gotten there. But in general, not, because there's a lot of different ways you could have gone.
Got it.
So I think no is the best answer. All right, let's roll here. Oh, in fact, here we are, JP, the fork slide. So we can have multiple different histories, as I said. You know, maybe in one case, Alice jumped out the window and it was awesome. In the other case, it didn't go so well. And some of these we can rule out immediately because they don't execute the state transition function correctly. That's what we were talking about when I was saying maybe I'm an attacker that wants to trick you into a malicious block. Some of these things you can say like, okay, Joshy, you didn't even execute this thing right. I'm not importing your block. Throw that one away. But it's also possible that we have multiple valid forks that we have to choose between. And so to get back to JP's question about why do we need to keep all of these really old blocks, the answer is because at some point you might actually change your mind about which one is best. And that's called a reorganization or a reorg. So we sort of like reorganize the blockchain. So imagine for a second that I had seen this block
and its parents. These three only. And I think this is like the best block so far. And then another block comes in and I'm like, ooh, this is the best block so far. And then another block comes in down here, a sibling. It's not an extension, it's a sibling one. And for whatever reason that I'm not yet telling you about, we decide, oh, this block is actually better. I think this is the real chain now, not the old one that I was on before. That's called a reorg. And the reason that you still need those around, at least, is because you never know how deep of a reorg you're going to go to, right? I at least need to keep this one around so that I can revert back to that state and then come to the new one, okay? Or maybe you imagine we're on here, and then we want to reorg over to this block, okay? Now I need to go all the way back to here. So this is why, in general, we need to keep some historical blocks around. Now, the older they get, the less you need to keep them around. And some chains actually have this notion of finality, which we'll talk about a long time from now, and I'm not going down that rabbit hole yet, where we can say like, okay, one block will never be reverted, modulo some assumptions, and so we can prune the old ones behind that. And some nodes do that. So like, maybe you set your node to only store like the 10,000 most recent blocks and like 1,000 most recent states, just to save disk space, because you're thinking like, I probably won't have to ever go back that far. And that's kind of analogous to what I was saying earlier about pretending like some other block is the genesis block, or is like my genesis block. Yeah. Mic up here, throw it right up here.
I have a question about the invalid blocks.
Yeah.
So imagine that there is an invalid block.
Yep.
Do you keep that also for future?
Probably not.
Okay.
I mean, the technical answer is no. Like maybe it stays in some cache for a little bit or something.
Okay.
But yeah, there's no reason to keep it around. It's like a waste of your time, basically. All right. So what I've focused on so far is this idea of cryptographically linking blocks together so that we know where they fall on the tree and executing the state machine in between. What I want to do now is start to look at a kind of more realistic block structure that's more similar to how you would do it like in the real world to make things a little bit more performant. So the whole big diagram here represents one block, and you can see that now I've kind of broken it apart a little bit into the header and the body fields, okay? So the header is a piece of like concise information that's in every block, and it has the same fields in every block, and it's basically the same size in every block. In some blockchains, it's literally the exact same size every time, and in other blockchains, it's like basically the same size within a tight margin. And then the real bulk of it is right here in the body. And so the parent hash is something that goes in the header. The state root that we saw earlier is also something that goes in the header. That's part of like other concise data. And there's a couple other fields that go in the header that I'm going to expand in the next couple slides. And then the body looks a little bit different too. Before, I was pretending like there's just one state transition in each block. And that is a valid way to build a blockchain if you want to, but it's pretty uncommon. A more common thing is to batch these things so that we have a whole bunch of transitions in each block. And what you do is you basically just put them in a vector or a list or an array or whatever your language calls that data structure. And then you execute them in order. So you would take the pre-state of the previous block and then execute this transition and this one and this one and this one, execute them all in the right order, and then you get out your post state for the block and put that in your block state root. So here's basically the same thing as my diagram, except expressed in Rust code. And this is from the Substrate code base. So we have this struct called block. That was that big thing I had. You can see it has this header type. It also has this extrinsic type, which is a pretty fancy name that basically just means state transition. So the block type is generic over a header type and a state transition type. Just makes sense, right? We all know we can track a lot of different kinds of state machines, and they all have different kinds of transitions. And then the fields are the header and a vector of these state transitions. And since it's a vector, they're ordered. So there's no question about like which one comes first. All right, so let's look in the headers. The exact content varies per blockchain. A Bitcoin header is a little different than an ETH header, a little different than a Near header, but they have a lot of things in common. The parent hash is the most important thing. If you don't have the parent hash, then you're not dealing with a blockchain. Beyond that, you maybe have a little bit of freedom to move things around. And I'll also say that the headers themselves are actually the hash linked list. It's extremely common to talk about the blocks being hash linked, where each block contains the hash of the previous block. What it really means is that each header contains the hash of the previous header. And I'll show that again in a slide or two. So here's just a couple of examples. In Bitcoin, you have previous hash. That's the most important one. They also include a timestamp. That's kind of a common thing to do. Actually, Substrate doesn't do that, but many chains do. And then like a version of the Bitcoin protocol. This is what allows like little modifications over time in a pretty rudimentary way compared to like what you see now. Transaction Merkle root. So this is something that we're going to talk about soon. This is a cryptographic tie into all the transactions that are in the block. And then you have some consensus related fields. So if we look over at the Ethereum one, it's actually pretty similar, right? Like the first two fields are actually identical. I guess they used a different name, but parent hash and previous hash both mean the same thing. That's the pink arrows that point back to the last block. Block number, that's a cool one. That's a convenience. Bitcoin didn't do that, but a lot of chains do. That way when you look at a block, you can easily tell like where, how far into the history of the chain does it go. Okay, transactions root, pretty similar. State root, we already talked about that. One interesting thing about Bitcoin is that they don't actually have a state root, and that actually creates some limitations and makes it a little harder to work with Bitcoin. But one nice thing about Bitcoin is that they have teeny tiny block headers that almost anybody can sync, so that's an engineering trade-off. And then, you know, again, some consensus related fields. So we can just look at Substrate's headers real quick. And, you know, actually, I guess I should say this is like a typical Substrate header. So you'll learn a lot about Substrate in the coming modules, but it's like a framework for building blockchains. So you can tweak pretty much anything about it. But, you know, usually when you come at it, you want to tweak like one or two things. And if you don't tweak the header, this is what it looks like. And being as Substrate's a framework, this is like a really, really nice model of like a generic, reusable, or like typical block header, you know, with nothing chain specific in it. So we've got the parent pointer, the height of the block, like what Genesis block is 0, the next one is 1, etc. That's like what the block number means. The state root, the extrinsics root, and then finally some consensus stuff. Yeah, Mike Tabota in the back. Right up here.
For the state and extrinsic roots, are they Merkle roots for over states and extrinsics?
Great question. Let me show it to you in this next slide. So your question was about the extrinsics root, right? And it is indeed a cryptographic witness to all of the transactions that are in the body. So I think maybe your question was, is it for states and transitions? And it's not for both, but we have two different roots, one for each. So we have like our state root, which is the, you know, cryptographic witness to the states, and then we have our extrinsics root, which is the cryptographic witness to the like the body or the list of all the transactions in there. And then you also mentioned the term Merkle tree, and so as a practical implementation detail, it is basically always a Merkle tree. That's pretty much how you do it. You like build your state into a tree, and then you put the tree root in the block, or you like use all of these transitions as leaves and build up the tree and put the root in there. Technically, it doesn't really have to be that. It can be any kind of cryptographic witness, like a Merkle mountain range, or just simply hashing the vector of these things. Now, obviously, if you just simply hash it, that's going to be way less performant and everything. So I would say, if you're a dev, maybe remember that it's a Merkle tree. But no matter who you are, remember that the most important thing is that it's a cryptographic witness. And what that means is that if I were to tamper or change any single thing about this body, anything at all, then the extrinsics root would look completely different. Just like when you change one little character in a file that you're hashing. Mic up here.
So my question is, so the parent hash is only a hash of the previous body, right?
No, not body, previous header. So like this parent header hash right here, that's a hash of this box right here.
Or the parent hash, I think, is a hash of the transition you mentioned earlier.
No, that's not what I mentioned. Or if I did, I was wrong. Let's go all the way back to this one. The parent hash is the very first thing we introduced, okay? This is the most fundamental one, and it's just a hash of the header that came before.
So meaning that the parent hash includes the transition, includes also the
Well,
state machine.
here we haven't even talked about transitions yet at this point, right? We're saying like, here's what I'm trying to say. Think about your simplest possible blockchain data structure. The only thing it has is some story-related stuff and the parent pointer. So before we even worry about whether this even is a state machine, whether it even has states or transitions, we already have a parent pointer. It's at a more lower fundamental level than anything state
So
machine.
basically meaning it's a hash of the header, the body, everything basically of the previous block, right?
So, not getting closer. We're getting closer. Let me get back to this diagram here. So, it is not a hash of anything except for the previous header. Okay, it's just like literally what I'm outlining in pink, like right here. That's what it is. Take this struct or JSON, throw it into your SHA-256 function. That's your parent hash. Now, maybe to get more to what you're thinking about, it is still a cryptographic witness to the previous state and to the previous body because this header itself has a cryptographic witness to the previous body. So I made this claim at the very beginning that we can check the entire integrity of our blockchain. We can check whether we're on the same chain simply by comparing our latest blocks. And this is exactly how. So if you imagine that I changed some little thing about this block, whatever, something in its digest or what digit here or the number, that's going to change its hash and that's going to break this link. Same thing happens if I change something in the body. Even though the transitions aren't up here in the header, imagine I just like change this little one so that instead of you sending money to Marcus, you're sending money to me. That sounds nice. But now that's going to change the extrinsics root. And since the extrinsics root is part of this header, again, that's going to change its hash and it's going to break this link. So if you're wondering, like, is this a cryptographic link to all the stuff before? Then yes, it is a link to all the stuff before. But if you're asking, like, is it the hash like of all the stuff before? Like, do I put all that stuff in the hash function? No, all you hash directly is the header, just the header. Let's get Bodo again. Throw that back there. Yeah, nice.
So just a question about the state root. So
The state root.
the states are, we agreed that they are not stored on the block.
That's
They're
right.
Stored like the node on like whatever the hard
Yep, they're
disk.
stored in the node, but not inside the block on a
Yes.
different database.
And this state, it hashes all the like are this, because this is just random data from different things, right? It's or
You're talking about state roots, right?
Yes.
And so the state root is basically like a hash of this state. Like, let's just pretend for a second that our state machine here is our like audio amplifier thing that we were doing. And so state 4 would be like, for example, outputting normal right now. So I take normal, I throw it through my hash function, and then apparently this is the hash of normal. And then like, let's say here we go like louder, quieter, mute, unmute. So we actually end up, well, no, that's a bad example. Let's say we go like, we were in normal, so we go like louder, quieter, quieter, mute. So now we're muted. So now this next state is going to be silent, right? And apparently this is the hash of, this is the hash of silent. I don't know if that's what you're asking or not.
yes, and in reality, the state already has a lot of data, right? Like this is
In a real blockchain, the state has a lot of data, yeah.
Yeah.
Hang on a sec, we'll get you in a second. Go ahead.
Hello, Johan here.
Yep, go ahead, Johan.
One question. I don't understand. How do you order which transition?
Yeah,
is on
okay, so
which
my
one?
diagram here is kind of silly because it's like a square, but this thing is just like a vector. It's like a one-dimensional list of transitions.
Yes, but for example, in the exercise from yesterday in point 2,
Yep.
there was this two switches example, right?
Okay,
When,
yeah.
when you press it off the first one,
Yep.
also turn it off the second.
Yeah,
right?
the weird switches. Yeah, that's right.
So if we apply something like that, in this case,
yeah.
the order of the transitions applied matters.
Yes, the order of the transitions applies matters in general. That's a good observation, but I still don't get your question.
Yes, my question is how do you figure out how to sort this?
It's not ambiguous. There's nothing to figure out. Like when I send you a block, I think it might look confusing because they're just like thrown into here. But what I'm really giving here is like a one-dimensional list. Like this is item 1, this is item 2, this is item 3, this is item 4. You just like iterate through the list and do them in order. Good question. All right, let's get the guy up front again. And edges, guys, people, don't feel, you can participate too.
So the state is actually not in a blockchain, but the hash of the state is in
in the
Exactly
blockchain,
right. That's exactly right. Yep. Okay. Anybody? Yeah. Here we go. All right. Left wing.
Maybe the question is a bit minor, but I'm wondering in this graph or in real blockchain, is the state root kind of redundant? I mean, the hash of, because basically the state can be calculated by the block.
Yeah.
And
yeah.
why this is included? Is it for explanation or?
So here, yes, it is basically a little bit redundant. So let's do a thought experiment where we don't have a state root in there. Like, as I mentioned, Bitcoin actually doesn't have that in there, right? The weakness that happens when you don't have a state root in there is that, like, when I send you a new block and you execute my block, you get some state. You don't know for sure that you got the same state as I do. You only know what you got. Now, presumably everybody else in the network will execute it honestly as well, just like you did, and get the same thing, and so therefore I'll eventually like get left behind. But the state root is really, really nice, just to, like, at the moment of import, you can be sure that you got the same data as whoever created the block.
So just to understand it a little bit clear, so it's like for calculation, easier calculation, but if somehow it's not included in the block, it's still possible. So just like Bitcoin, right?
Yeah, that's right. And
Okay.
and there is another reason too that I was trying to avoid, because we're not quite there, but since you're digging at it, I'll just foreshadow a little bit. The state root actually makes proofs for light clients quite a bit easier. And so I haven't talked about light clients yet, but when we get there, maybe bring that up again.
Thank you.
Okay, let's keep rolling. Thanks for the questions. Yeah, okay, so extrinsics. So this is the like substrate world jargon for what I've previously been calling state transitions. They're basically like little packets of information, and they might have signatures attached. Typically, they probably will. If I'm trying to send you some money, I probably need to sign that to make sure I can spend it. But there are some edge cases where there aren't necessarily transactions. And just to give you like the most classic example I can think of, it would be like the Coinbase reward. Like if I create a brand new block and my chain allows me to mint myself some tokens, like in Bitcoin, you get to create yourself like, I forget how many halvenings it's been, but like originally it was 50 new coins. That transaction doesn't need a signature. It's valid just because the miner put it in the block and has the right to give themselves the new issuance. And another classic example would be like a timestamp. Maybe you want to have a transaction where the miner just includes a timestamp into the block. It's kind of like a public good. Everybody has the timestamp then. And it also doesn't require a signature. It's just valid by virtue of the block author put one in there and always allowed to put one in there. Yeah, let's get the mic over here.
Are those kind of transactions are called inherents?
In Substrate, they're called inherents. Bingo. Yep, that's exactly right. But don't tell Kian that I already told you that, okay? You got to look impressed when he says that. Yeah, so I think this is maybe the main way that I would think it. These are like function calls to your state transition function. Each one of the extrinsics is basically calling your next state function with some data in there. So I'm going to take a tiny little tour away from block chains or block trees. So far, this is a block tree. It could, we could choose maybe like this is the best chain that we're thinking so far. But there's another data structure that's very similar that I want to mention that some like blockchain, technically not chain projects use, and it's called a DAG, a directed acyclic graph. And Marcus, you were asking about graphs yesterday, so good foreshadowing. So here's what's different about a DAG. DAGs are more general. Blockchains are DAGs, but not all DAGs are blockchains. And here's the difference. So what's up with that thing that I added there? Anybody see what's weird about it? No cycles, because it's acyclic. Someone said it though. 2 parents. Yeah, that's right. It has 2 parents. So there are a lot of things complicated that you have to deal with when you start working with DAGs. But if you can deal with the complications, there's a lot of things that are really, really awesome about it. Let me give you an example. Imagine we have some financial system over here. People are paying each other in every block. Tokens are moving around. And then maybe up in this block, we have a whole bunch of stuff about like us PBA folks like buying taxis here in Hong Kong or like buying lunch here in Hong Kong. And then over down in this block, we have a whole bunch of stuff about like people in the United States doing their economic activity. And then maybe this block has like a random transaction that doesn't have to do with any of that. And the point that I'm trying to make is that all of these transactions are not related to each other. And so we really don't want to have to choose one side or the other. We'd like to say all of those transactions are valid. Why not include them all? Why make anyone redo them? And with a DAG, you can do that. Anytime you don't have conflicting transactions in here, you can join back together, and that way you got to like execute more stuff in parallel. Get the mic over here.
When you do have like diverging paths,
Yeah.
how do you infer the state?
So you still have a state at every block. So, you know, like we would calculate the state of this block the same as we always did, and here the same as we always did. Now, the state of this block is what's hard and what's new.
I mean, before we even talk about that, like,
Okay,
so,
yeah.
I mean, I guess, yeah, it is necessary to have the conflict, but because before you do that, then you have like different stories, right?
That's right. Yep. Yeah. This is a great way to say it. Okay. Let's make it like a regular English story. So like Alice and Bob meet, and then they high five, and then Bob goes to yoga, and then Bob goes to work, and Alice went home and slept, and she still stayed asleep, and then the sun came up the next day. Alice's stuff and Bob's stuff are totally orthogonal and both totally compatible. And in that case, we can put it back together. And so the state would be like, I forget what I said, maybe Bob was at work and Alice was still sleeping, plus whatever happened in here.
Okay, so let's make it like, I don't know.
Yep.
Alice was born.
Yep.
Alice died. No, sorry. Alice was born. Alice went to lunch.
Went to lunch.
And then Alice died.
Yep.
And then Alice married.
Yep. Okay. So why is your example different than mine, in case anyone didn't see?
Because Alice cannot marry from death.
Yeah. Depending on your cultural norms. So in that case, you can't have a block like this, right? In DAGs, you can't just merge any arbitrary branches you find. You can only merge them when they're compatible or non-conflicting.
But I'm saying that like this is a divergence of stories that are conflicting.
That's right.
So at what point do they get eliminated?
So at what point? Well, just like in block, you know, you can always reorg, right? So maybe they never really truly get eliminated, but at any given moment, you have a chain that you think is the best. So let's say like you were following this chain. Okay, so this is the one where Alice died, I think. And then maybe later, like for some reason, you change your mind and you start following this chain instead, where Alice got married and has a beautiful house or whatever. But at some point, someone sends a block across the network that's this one, and you validate it, and you say, no, this is invalid. This contains conflicting transactions in its history.
Okay, because it's referring to both of them, and
Yeah,
it's saying Alice had kids, let's say.
Yes, exactly.
And then you check, and it's like, but Alice is dead.
Exactly.
And then
exactly
you say,
right.
invalid.
And so this is, you've pinpointed the crux of why DAGs are hard, because whenever a block like this comes, you need to check, are they compatible? And sure, here maybe it's not so hard, but maybe these forks were disjoint for quite a long time before a common ancestor. Yeah, Marcus.
More or less. I think you might cover this later, but more or less, I do want to like bring this up now. How would a hard fork in such a graph work in this instance? Like, let's say you have transaction A and transaction B, for instance, and the community decides that transaction A is valid, whereas transaction B is invalid. So more or less, we would want to go with the transaction history that involves transaction A and so forth. How would that work?
Yeah,
in such a graph?
that's a great question. I'm with you. So I'll give you the short answer now, but actually maybe bring this up again when we're in the forks lecture because we can follow it a little bit better. So like if your fork is something like the rules change at a certain height, maybe like all of these blocks use the old rules and all of these blocks use the new rules, then you just have to enforce that the fork was followed correctly in each path of the history. But also if you have like a contentious fork where the community doesn't agree, then obviously you need to like, you would never merge the two conflicting sides back together, right? They're split forever. Good question, thanks. And we can talk more about that once we've sort of built up forks formally. Yeah, let's get Carla.
Just conceptually with the stories,
Yeah.
in terms of the actual transactions on the blockchain, I'm finding it hard to reconcile these between stories and finding, for example, analogies with Alice getting married or dying.
Yeah.
So, for example, if I'm just going back to the blockchain, cryptocurrency to
Yeah.
Jessa, and then
Yep.
maybe to Mikhail or
Yep.
something like that.
Yep.
Is that what we're saying? Okay,
Exactly
they're both doing a transfer of cryptocurrency. That's the same block.
Yeah, so you're on something exactly right. So like he was giving the example of like, you know, easy to understand at a human level, like Alice died versus whatever else. Your example is a more technical one that's perfectly analogous. Like let's say you have 10 tokens here, and then in this block you send those 10 tokens to Bob, and in this block you send those 10 tokens to Charlie. This is a classic double spend, and those are conflicting, and now we need to decide. We can't merge those histories back together. Yep, so yeah, great question. And then maybe just to make the story connection a little similar, like the way that the story works in a cryptocurrency, I'm not going to say it's like an entertaining story, but the story is basically like Alice sent 10 tokens to Bob, and then Bob sent 10 tokens to Claire, and then Dave sent 4 tokens. You know, it's like a boring story, but it's just a list of financial transactions. That's the story we're telling. Yeah.
Hi, Sukhmeet again.
Yep.
You are mentioning DAG, so we have moved, and that's a very good thing. So the first structure that we picked up was Merkle trees.
Yep.
Now we picked up DAG. So just to bring in context, I don't think they are hard per se, but what I would say is they are more complex. Like Merkle trees were more complex than the previous structure, and they bring in the ability of having very fast calculations done on them. So blockchains more or so are moving towards DAG. Is that a fair statement?
I'm a DAG enthusiast. There's a lot of people that aren't, though. There are a lot of complexities with DAGs.
Yeah.
Yeah. And security implications sometimes, too. So, yeah, I mean, I think you're thinking in the right direction, though.
Merkle tree got, like, there were so much issues.
Wait, but I didn't actually get what you meant about Merkle tree. What are you saying about Merkle tree?
See, Merkle tree was a complex data structure when it came around. Same thing, DAG is the next iteration of blockchains adapting a new.
Yeah, okay. Maybe if I can summarize, you're making a thesis here that like, yes, DAGs seem complex right now because we're just starting to work with them, but we're probably going to understand them, and maybe they'll like be the next blockchain in a couple of years or something.
Yes,
Right,
they have their advantage.
Reasonable thesis. Yeah, let's see how it works out. Thanks for sharing. Okay, so we're getting near the end. I've basically finished the parts that I wanted to say about the blockchain data structure, and now I'm going to briefly marry this concept up with P2P networks. So now that I'm thinking about it, we're kind of gluing together like our state machine, our blockchain, and our P2P all in this one lesson. So the servers here sitting connected by links probably looks kind of similar to some of the figures that I showed like in my Web 1, 2, 3 series. And what I'm trying to demonstrate is that when you're in a P2P network, there's no server you can call up. There's no like, you know, official napsterdata.com or whatever. Everybody has their own view of the data. And so everybody here has their own view of what's going on in the blockchain. So we can see like this person has like a pretty complete view. That's a whole lot of blocks here. This person down here has a little bit different view. It kind of seems like maybe they're missing these 2 blocks, and then maybe they have this extra block. And then this person over here has like a pretty limited blockchain. They must have like poor bandwidth or something, because it seems like they haven't heard about the most recent blocks yet. And then this person up here, maybe they're like pruning blocks or something. You know, it seems like maybe they said they don't want this one and threw it away, or maybe they never heard of it or something. And so when you're in a P2P network, what we're trying to do is actually reach a similar view of the blockchain. What we want it to be is like eventually consistent. And what that means is we hope that for blocks that are way back in the history, people have pretty much agreed those ones are in the chain, they have been for a long time, they're almost certainly going to continue to be. But near the tip, there's still a lot of action. It's like if you're walking through the forest with your friends, not totally sure which way to go, you can pretty much agree where you've been. And then like people are saying like, let's go this way, no, let's go that way. And then maybe you like split up and take different paths for 5 minutes and then decide which one you're going to go with. And all of this interesting stuff is happening around the tip where you're like probing the different paths that you might walk through. And then I guess I should also say, like, there's gossip happening on this network, right? So if one server, like this one, adds a block to its chain, what it should do is gossip it out to the other servers, maybe all at once in a naive way, or maybe using the fancy protocol that Sean was talking about yesterday where they can do it more efficiently. And then, so let's say, like, maybe the node here just authored this block, so it gossips it out to the nodes that it's connected to. And then they do that process that I described earlier, where they take their previous state and they take whatever transitions came from this block and they execute them. And if it's a valid block, they add it. And then in this case, maybe this guy also gossips it over here to this person. So, okay. And so these servers that are sitting here are typically called nodes. This is another graph theory word. So a node is basically like a piece of software that participates in a blockchain network. So think about like your Bitcoin node or your Polkadot node or your Monero node. And its jobs are these. And there's a lot of them there. And not all nodes do all of the jobs. So you could think of like an archive node or a full node or a validator node or a light node or anything like that. And basically for any kind of node that you describe, they're doing some subset of this job or maybe even the complete subset. So pretty much every blockchain node stores block headers. That's like the most basic thing that you can do as a blockchain node is store the block headers. Now, if you're a full node, you might also store the complete blocks, you know, with all of the transactions in them. You might also store the states. I would say a lot of nodes store blocks and states, at least recent ones near the tips. And, you know, why are you storing all of those, all of that data? Maybe it's because you're a miner or a validator, someone who wants to author blocks. That's one reason. Or maybe you're storing all of this data about the states and the blocks because you're an RPC node. Maybe you want to let people's dApp front ends and you want users to be able to call up your node over an RPC endpoint and provide data. You know, like maybe I'll query a node like, hey, Ethereum node, here's my address. Can you please tell me my ETH balance? The way that would work is that I would call up some node over an RPC. They would look into their states that they have stored, and then they would tell me like the answer. And so to get back to Zeke, I think it was Zeke that was asking about the state roots. One reason that it could be really useful to have a state root in your block is because if you, let's imagine this. Let's imagine there's some full node out there that stores all the blocks and all the states and everything. And I don't have that much disk. I just have a small, you know, maybe I'm running on a phone or whatever. All I can afford to do is store block headers. But then I want to know my balance. So I call up a full node and I say, hey, full node, what's my balance? And they come back and say like, oh, you've got like 10 ETH. Well, I kind of have to trust them because I don't have the data myself locally. But a different thing that you could do, and what light clients typically do, is you say, okay, I have the block headers. Full node, can you please tell me not only my balance, not only the data, but actually a Merkle proof of what my data is, of what my balance is. And you guys know about Merkle proofs. You did it in module 1, right? So my balance is the leaf that I care about, and then you find the path back to the root and send the proof with the sibling nodes. And I actually know the root because I have the block headers myself. So if I have the block headers, I no longer have to trust the node to tell me my balance. I can check the proof, and if it matches up, then I know they didn't lie. Okay, yeah.
Wait, so then how, if you don't have block headers in Bitcoin, how do they do that?
There are block headers.
Sorry.
Oh, you don't have state roots though.
Sorry.
Yeah, light clients are very hard in Bitcoin. Honestly, I don't know how they work. It's pretty hard. Actually, well, Bitcoin's UTXO, so they have this thing called simplified payment verification. We can dive into that, but not right now because I'm not prepared right now. That's a great question though. And your observation is right that that's harder when there's no state root. Oh yeah, I guess I already told you about the types of nodes. I mean, so maybe just to tell you what they mean in general, like I think a full node is kind of like the most default node, like the standard thing. It keeps the blocks and states. It doesn't author. There's also light nodes. These are the ones that only sync the headers and kind of rely on those proofs for other data. And then these are like your miners and validators. You know, authoring nodes, they do everything that full nodes do, plus they create new blocks. And then there's archive nodes. These are basically full nodes who keep all of the blocks and all of the states for the entire history of the blockchain so that they can be easily queried. And a lot of times if you're running an archive node, it might be because you're somebody like a block explorer, and you might not only run the archive node, but like also run an SQL database that indexes all the data or something like that. And then finally, RPC nodes are the ones that kind of like are out there to just let people query their data. Yeah, Carla, go ahead.
In terms of the data storage, it seems like there's a lot more data that's out there compared to a centralized system because everyone needs to keep, from what I see.
Yeah, for sure, yep.
But we learned in like 101 that you can't reverse a hash.
Yeah,
for the
one-way
underlying-
function, that's right.
For the pre-image.
Yep.
So who's storing the pre-image?
Well, you're storing the if you're storing a blockchain, the hash is there. It's like the hash of block 1 goes into block 2. So if you, let's say I pull up some block, here's block 2, right? There's a parent hash in there, right? And you're saying like, where is the pre-image for this hash? Well, it's block 1. It's also in your database. You start with the pre-image, basically. You always get the pre-image first and then get the hash.
Okay. So the whole data set, every single piece of data, like images, everything is all.
So if you, I mean, okay, here, let's go back a little bit. This seems like a pretty good question, so let's dig in a little bit. Oh, wow, not that far, holy moly. I wanted to go to, I think I want to go to this one. No, I think, all right, let's go with this one. So the only thing I don't like about this figure is that I wish the blockchain were longer, but we're just going to have to use our imagination and pretend these are all the blocks near the tip, and then this is the long history that we can't fit on our disk, okay? So here's a hash. Its pre-image is this block right here, okay? So if you keep the whole blockchain, then you do have every hash's pre-image. Like you can start at the, at the tip and say, here's a hash, here's its pre-image, here's a hash, here's its pre-image, here's a hash. If this weren't the Genesis block, here would be its pre-image. But if you decide to like start pruning, if you decide like, oh, I don't have enough disk space for all this and throw this away, then yeah, like you don't have this pre-image stored on your disk anymore. You probably don't need it if you decided to prune it, but if it turns out you were wrong and then later you do need it, then what you would do is you would call up like an archive node or someone and say like, hey, can you please give me the Genesis block? And they'll give you some data, and then you can check whether it's the real block you were expecting by seeing whether it matches, whichever block you do have.
Okay, thank you.
Yeah, thanks. And there's a question all the way at the back of your section too. Can you throw that mic back there? Carla, can you throw that mic back there? Thanks.
Sorry.
We talk about syncing.
I'm just going to go in between.
Joshy, we talk about syncing because you're kind of alluding to it right now.
Talk about syncing. Yeah, we can not explicitly.
Yeah,
I'll talk about it in a second.
This is just a question in general from what I've noticed or I'm seeing in terms of the trend. So you mentioned something about indexers, and essentially, I guess that relates to having the database stored, and people want to query for particular transactions and addresses. Do you think that I guess we still need to have more optimized databases or kind of data structures so that we can query these things better?
I don't really have an opinion on that, to be honest. Is there a problem that you see? Do you think that?
Oh yeah, I mean, the different kind of blockchains are kind of pursuing that, right? Avalanche currently just improved on the read and write of their DB as well, and a lot of people are talking
okay,
about...
but hold on though. If you're talking about Avalanche, you're talking about part of the node, right? You're talking about
The
their
DB.
DB. The DB that stores like the blocks and the states and stuff, right?
Yeah.
So that's separate from like an indexer, I guess.
Oh, okay. Well, sorry then. What do you mean
I
by
mean,
indexer?
the better the database, the better for sure. Like I want the best
Sure.
database we can get, absolutely.
Then what do you mean by indexer in this context?
So, yeah. So
Sorry.
an indexer is also a database, but I guess what I would say is like when you're talking about a blockchain nodes database, there's like a more fundamental database that means. So let me try to distinguish the two. What I've talked about on the slides so far is like my blockchain nodes database. It has blocks, it has states, it has headers. There's also another thing called an indexer. And if you want to run an indexer, basically what you're trying to do is provide a service so that anyone can come to you and ask you questions, very specific questions, and give them answers fast. So, for example, if I wanted to ask you, like, here's 6 accounts, what were their balances 3.5 years ago at this specific block? If you're just a blockchain node, you're going to have to do some digging to get back into those parts of your database. But if you're an indexer, you've taken that entire blockchain, and as the blocks come by, you've dumped all of it into an indexed SQL database, a separate database than the normal blockchain one that can give those answers a lot faster. It's basically copying the data into a different centralized format.
Got it, cool.
Yeah, good question. Thanks a lot. Yeah.
Thank you. This could be a stupid question, but I was thinking, okay, you have all those blocks. Imagine that I made a mistake and there needs to be a block somewhere in between. So Alice jumped out of the window, but first she needs to open the window, so I forgot to put it in there. Does that also mean that you need to recalculate everything that is behind that?
Okay, so first let me answer your question like from the blockchain data structure perspective. Which one do I want? I think I want this one. So you're saying like if it turns out that I wanted to do something else in here, like I did this and this and this, and then I'm like, oh crap, like 3 steps ago I was supposed to do something in here. So from a blockchain data structure perspective, if you're making this data structure, then yes, these 2 blocks are garbage now. Throw them away. You need to go back here and put in the thing you wanted, and then you can reapply these same transitions. But you can't just reuse these blocks because they have the wrong parent hash, right? You need the parent hash of the thing you inserted in here. And it's same, like the states, maybe they'll be the same, but in general they won't, because probably whatever you did in here affected the state in some way. So now let me ask it, or talk about that in like a P2P blockchain network kind of way. In a P2P blockchain network, what you're doing there, you're actually creating an alternate chain. Let me put it that way. So maybe here's your like original story on top. Alice woke up and then she went to work and then she came home. But what you actually wanted was like Alice woke up and then she brushed her teeth and then she went to work and came home. It's just different branches. They're both valid stories. And so then what you need to do is like this is the problem that Harari was talking about. The difficulty is getting everyone to believe your story, especially if they already know the one where she didn't brush her teeth. Good question.
One question. Can you explain a little bit more about like clients?
Wait, who's speaking? Here. Oh, got it.
Yes, I want to understand like clients, maybe some use cases.
Oh, yeah. I mean, so, okay. If you think about an ideal world where compute is cheap or free and disks are cheap or free, you should run a full node. That's the best blockchain-y thing you can do. You should run your own full blockchain node. But disks are not free, and blockchains are big, and bandwidth is expensive. And so what people sometimes do is they say, I'm not going to run my node. I'm just going to have my little wallet here. I'm going to connect to your node. You pay the cost. That's very dangerous. It's going to save me some money by not running my server, but it's also going to allow you to lie to me, and I would never know. So the intermediate thing that you can do between the extremes of running your own node and not running a node at all is you can run a light node, which only syncs the block headers. That's still very important. The header is the backbone of the blockchain. It's the thing that has the parent hashes linking it all the way back to Genesis. What's nice about it is that it's small. It's not nearly as big as the whole chain. And if I run the light node, I'm not self-sufficient. I don't even know my own balance without your help. But the beauty of syncing the headers as a light node is that when I call you up and ask you, hey, can you please tell me my balance? You can't trick me anymore because you're going to tell me my balance and I'm not going to accept it unless there's a Merkle proof. And since I have the block headers that has the state root, then I can check the Merkle proof.
So for example, in a DEX, there is a good use case about it in there, like maybe Hydra DX, something like that?
I don't know that connection exactly. DEXs are cool though, definitely. Yeah, so we can talk more too if you have like a specific application there. Okay, I'm gonna try to wrap up because I'm getting tired. I think you guys might be too. Oh, I wanted to talk about syncing because yeah, Andrew brought that up and I think that's a really good point. So syncing, it stands for synchronizing the chain, and basically what it means is if I'm a new node that comes in and joins a blockchain network, like, oh here, in fact, you know, maybe this guy is syncing right here. Maybe this is a new node who just joined. When you're a new node, you don't know anything except the state machine and the Genesis state. And if it's an old blockchain, you've got a lot of learning to do before you're caught up with the current state. And so what you do when you're a brand new node is that you find some peers, probably through a boot node or some process like Sean was describing yesterday. And then once you have some peers, you start asking them like, hey, what's block 1? Hey, what's block 2? And they all, you know, they're telling you all of these blocks and you're checking them as they come in. And eventually, then you get up to the tip of the chain. And the reason that I chose this guy as the one that was maybe syncing is because when you come in and sync, you're typically going to get a linear chain for a long time. You're not going to need to know about all of these like interesting forks that happened back deep in the history because they've been settled. Okay, yeah. Question in the back. Let's throw a mic back here.
Yeah, concerning syncing of the chain.
Yeah.
Okay, for example, I am Risha. So the issue is why should we start from Genesis? And if, for example, I want to sync with Kusama, right? Why should I start from Genesis and then build up until the latest header and go on and continue, while I can just, we have the finality of certain block of certain height. I can just use that as my Genesis and continue building up. Why should every start from scratch?
Yeah, so let's set aside finality for now. I'll address that at the end, but let me start with the more fundamental thing, because not all blockchains even have finality. And so basically, like, what you're describing is pretty reasonable, and it's pretty common for people to actually not sync the whole chain. What you can do is like download like a snapshot of the state at some block and sync from there. The reason it's always a trade-off, right? That is better because it's way faster. It takes a lot less disk, a lot less compute, but it's also less safe because all you know is that this is like some state and some chain. You don't know that it actually started from the Genesis state that we all agreed on. The only way you can know that is to actually verify block by block that the chain links the whole way. Now, that being said, like as a chain gets longer and longer, you can usually get pretty good consensus. You know, like maybe just dial up 10 nodes and look at like 2 block explorers, and if they all say that block 1 million is the same thing, it's maybe pretty safe to start from there. But you know, in theory, you are still exposing yourself to like maybe all of those 10 nodes and 2 explorers that you contacted are like colluding or eclipsing you or something like that. So that's the value in syncing the chain from start. Now, you also talked about finality, and so we'll get to finality eventually, but just as a quick primer, it means like if we say this block is final, it means that as long as some math assumptions stay true, we'll never revert it, we'll never reorg away from it. And you can sync from the latest finalized block, but let me ask you this question. Who do you know who the people that are supposed to finalize it are? If you haven't synced the chain from Genesis, you don't even know who's allowed to like be saying this is final. So that's why like the most fundamental thing is always syncing from the start. All right, one more in the back.
So I think I understand likelines conceptually. So then, technically speaking, what the likeline does is it gets the root. Yeah, so technically speaking, the likelines get the root hash, but then they also ask other likelines or nodes.
Full nodes, yeah.
Okay, to like give them the root hash and compares it.
So they have the root from the headers, and they ask other full nodes to give them proofs. And you know how to check a Merkle proof, right? If it matches the root and matches the path.
Okay, thanks.
Yeah, you're welcome. Yeah, what's up, Aaron? Oh, okay. Can I do just like a couple? Do you want to do it right now? Okay. Not yet. Almost there. I have like 2 last slides, and this one's about block space. I'm going to tell Rob you almost cut off the block space slide. So first thing I'll say is that block space and core time are roughly analogous. I would say they're roughly equivalent. They're very similar concepts. So in Polkadot ecosystem, you'll hear people talk about core time a lot, and in the broader blockchain space, you'll hear people talk about block space a lot. So I want to let you know at the outset that core time is basically Polkadot's worldview on how you should quantify block space. And not every blockchain takes that same perspective. So block space is basically a resource that's created and often sold by these decentralized P2P-based blockchain systems. And that makes kind of sense if you were thinking about economics, like there's some resource, we'll call it block space, there's going to be a market on it, okay, but now that we're like thinking about blockchain, it's like, okay, well, WTF is the block space? Like what actually is it? And it is like a pretty good name. It's the space that's available in the blocks for users of the system to contribute to the story, to put their transactions in. If we have some big global story that we're all agreeing on, you can imagine that you might want to contribute to it. I might want to get some transactions, some pieces in the story that say like, and then, Joshy like came to Hong Kong or like did this cool thing or got married or whatever. Like that's kind of like fulfilling as a human, right? Like you want to be part of the story. That's what we're here to do. The thing is, the blockchains only produce so much block space, and so there's usually competition for who gets to get their stuff in there. Where should I say this? I guess I'll go back to here. So if you look at this structure, like I've said before, one very simple way and reasonable way to quantify block space would be to say like, there's only room for 4 transactions in each block. Every block can have 4 transactions. Any more than that has to wait till the next block or a future block. And so you can imagine if there's a lot of people coming in here saying like, man, I really need to get my birth certificate in the story, or I really need to send this money, or I really need to vote in this prediction market, or I really need to swap this shitcoin, or whatever. They might really want to do those things, and so they might bid against each other for the privilege of having their transaction included in the next block. Now, counting transactions is a pretty simple way to do it. There's other ways to do it. We could say maybe there's only 1 megabyte worth of space in the block. So if this transaction's huge, maybe it's the only one that fits. But if they're tiny, maybe we can fit 100. That's basically approximately how Bitcoin does it. Another way that you could do it is that you could have a VM like Ethereum, and you could take every opcode in that VM and say, like, okay, this opcode costs 1, this opcode costs 9, this opcode costs 4, and then meter, sum up as you're executing each transaction, and then you can say, like, we can only have a total of however much, like, metered execution. That's what Ethereum does. And then the core time way, as that Polkadot does, is more based on time. How long does it take to execute this thing? So it's not addressing like the disk space usage so much as the amount of time to write something to a disk. There's a million ways to do it. I'm not saying any one of those is best. I bet none of them are, and we'll come up with something better. But they're all attempts to quantify and accurately like price this resource called block space. Boda. Let's get a mic in the back row. Who's got the mic? Oh, you got it.
How can I quantify the time? I mean, it depends on the hardware that's running the.
Oh, how can you quantify the time?
I mean,
Same
depends application on different hardware.
Just reference hardware. There's no fancy. That's it. Reference hardware. Okay. Yeah. Let's throw that up here, Boda. Oh, did you have a question too? Okay. Yeah. Just check it up then.
So in this case, like when you want to compute time of some algorithm or something, then you might need to run through it. Is it not like that?
You might need to what?
You might need to execute it first to.
Yeah. So okay, this is going to be covered in a lot of depth in Sean's module, but the simple answer is yes. Like if we're doing this core time thing, if we're going to quantify our block space based on execution time, then yeah, you need to benchmark that thing before you launch your chain so that you can like launch an economically sound chain.
Okay.
Over here. Mike over here.
Do we try to push this idea to every validator that hey, run the higher end server so that we get more core time, or do we just take it whatever they run? So higher end hardwares will give better execution time. So do we push this idea to validators that hey, run the higher end?
This is a really, really good question. So let's say we're quantifying our block space in time. Let's say we have like 5 seconds for every block or whatever. Well, obviously I can execute a lot more instructions in the same 5 seconds on like a supercomputer compared to my like gaming laptop compared to my smartphone, you know? So why don't we just have the validators run the nicest hardware that they can? Anybody? Just yell it. Lower decentralization, yeah. So the argument is basically like this. If being a validator requires really expensive hardware, there's not going to be a lot of people that can afford it or maybe are willing to afford it. And so you're going to get fewer of them. And you're going to price out like, you know, home validators or small scale validators or something like this. So this is actually, like Bitcoin takes this argument to an extreme. This is why Bitcoin Core has their like 1 megabyte block limit or whatever. Because they want you to be able to run a full Bitcoin node like on your Raspberry Pi in your garage and a satellite or you know whatever, which they're on the right spectrum, right? They understand that argument. Maybe it's a little too extreme, maybe not. You know, that's a decision for you to make for your blockchain. But that is the fundamental trade-off. Like you can get a crap load of you want to know how you get the most throughput, use the best computer in the world, and there's only one, and then there's only one validator. So that's kind of like the edge case. So that's all to say you're exactly right. That's the trade-off. Do you want to speak again?
The one who especially runs the higher end hardware, do they get any advantage?
So yeah, so you're saying like if, let's say there's like 100 validators out there, obviously we're not all running identical hardware, there's going to be some best one and some worst one. So they don't get any advantage. And the reason is like, as a validator, you have a bar that you need to clear. And that bar is that your computer needs to be fast enough to execute these blocks in 5 seconds. And if you meet that, that's great. You've done it. You can be a validator. And if you go above and beyond that, it doesn't matter because other people can't execute those then, right? If you build up a block that has a whole bunch of transactions, just because you can run it in 5 seconds and then you gossip it out, everybody else in the network is going to say, this block is overweight. I reject it. It doesn't run in 5 seconds. I don't care what you think. I can't run it in 5 seconds. I reject it. Mike in the back. Here it comes. Might have some hops. Nice.
Hi there. So this concept of time, like, I'm still not getting how it works. Like in Ethereum, having different opcodes have different prices and pricing it like that, that is subjective. But like the concept of time is even on different machines, they have slightly skewed clocks. So what do you mean when, hey, I don't run this block in 5 seconds and I reject it? Like maybe it's 4.9.
Yeah, I mean, you summarize like Ethereum's method, right? You meter it as you go. Yep. And you're right that like the execution time will be different on various hardware, but like the way it works is you say like, okay, our block space limit. So in Bitcoin, they say like the block can only be 1 megabyte, right? Because they quantify block space by disk space. In a time model, we say like, okay, our blocks can only take 5 seconds to execute on this very specific reference hardware, right? And people basically know how much you can do in 5 seconds on this reference hardware because we've benchmarked it and everything. But then where the rubber hits the road, like the bottom line at the end of the day is like, can my node execute this thing in time? And if not, I have to throw it away. So yeah, maybe like it's possible that maybe there would be, you could construct a block where you get like half of the nodes can execute it in time and half of them just barely can't. And I know that there's systems in place in Polkadot to handle this. I don't know exactly how they work, and you'll have to ask about it in like, Sean would be the guy to ask.
So
probably.
there isn't like any objective view, only subjective with high probability of it.
Well, but you're hearing about the reference hardware, right? That's like that's the most objective part. That's how you make it objective. But I'm not here to shill core time, okay? I'm just here to. So yeah, if that doesn't sound to you, that's a valid position to have. Okay. So yeah, so I wanted to just look at this diagram here. I'm basically making an analogy between Web 2 and Web 3 over here. So in Web 2, you have something on like AWS or Google Cloud or some server that some server operator owns. And then there's some application that you wrote on top of it. Maybe it runs in Rust or whatever else. And then there's like the user interface. And so in blockchain, it's actually really similar. We replaced the server with the blockchain network. And instead of selling, like server hours, we're selling block space over here. And then you have like your dApp that you wrote in Solidity or that you built on your Parachain or whatever. And then you have the user interface that runs in the browser. And so we have like really, really similar stacks here. And we're also starting to realize that it's really similar business models. A blockchain sells block space in a similar way to how AWS or Google Cloud sells like server time to consumers. So I would say this is the takeaway about block space. And then I put a bunch of links there that you might like to. So this is about the transaction pool. And so the transaction pool is occasionally known as the mempool. I think someone used that term earlier. In Bitcoin, they usually call it the mempool because it at least originally was all in memory and maybe still is. But a better term, I think, is the transaction pool because it's a pool of transactions. And specifically, it's a pool of transactions that are not yet included in any blocks. It's the transactions that people want to get into blocks that are queued up competing to get into blocks. And the transaction pool is actually where the block space market operates. So if you're at one of these nodes that's an authoring nodes, the nodes that add new blocks into the chain, then what you're doing is running one of these transaction pools. You have a whole bunch of transactions sitting in there and you allow people to call you up with new ones and say, like, for example, I'd like to get my transaction into an upcoming block. Can you please put it in your pool? And then when it's your turn to author a block, what you do is you go to your transaction pool and you look at all the transactions before you and you say, all right, which of these are going to make me the most money? And those ones are the ones that you put into the block. So in some blockchains, there are like formal official ways to operate the block space market. Like maybe you're officially supposed to take the transactions that have the highest gas price or that offer the most tip compared to how many bytes are in them or something like that. Basically, typically what you do is take the transactions that offer the most fee per block space consumed, however your chain measures block space. But the interesting thing is that the transaction pool operates entirely off-chain. It's not something that we're going to get consensus over. It's not something where anyone can really like check your work or know what algorithm you used when you selected transactions. So what you do in practice is you take the ones that make you the most money. And that's actually the origin of this concept of like maximal extractable value is choosing the transactions that the miner can selfishly profit off of the most. And so I guess basically what I'm saying is, like, as a block author, you're constantly looking at this thing, reprioritizing it. Every time a new transaction comes in, seeing like how valuable is this one to me, and then when it's your turn to author, you get to basically decide what goes into the next block. And so if you're one of these authors, you're actually in kind of a privileged position because you get to see the future a little bit. Most people don't know what's in the next block until the next block comes out. The best they can do is guess. But if you know that you're going to author the next block, you know what's going to be in there already, or at least you can, and you might be able to kind of take advantage of that a little bit. Yeah, question in the back. Throw that mic over, please.
Yeah, Mauricio. So, okay, the mempool is not in the, okay, it is off-chain, right?
Yes, it's off-chain.
So one thing is, and the miner can reorg the transaction, right? In the mempool, can reorganize.
So yeah, so I wouldn't use the word reorg because that specifically is what we say when we're like changing chains. But yeah, they can like reorder or reprioritize.
Yes.
That's exactly right.
So one thing is, after, okay, and the transaction define the state transition.
That's right.
Right? So if the miner reorganizes, reorders, and he produces the block, and then and other people must confirm and reach consensus and whatnot. The issue is, if I reorder my transaction, let's say 145, and other nodes have 154, we cannot, how can they re-execute the transaction and reach the same?
So no one changes the order of transactions once they're in blocks. That doesn't work for exactly the reason you described. So where the reordering happens is over here. So like this is a blockchain, right? There's 5 blocks in this chain so far, okay? And let's say I'm a miner or a validator and I have my transaction pool. Let's just pretend it's like over here. And it's swimming around with a whole bunch of transitions that aren't in any block yet. This is where I can do the reordering in my own little private notebook where no one's looking. And then eventually it comes my turn to author a block. So I do. And at that point, I have to commit. I take the ones that I want, whichever ones are going to make me the most money, and I put them in the block. And they're stuck, right? Because there's literally an extrinsics root here. No one can mess with it or it'll change it. So once it's out, it's out. That's a really good question. Yeah. Okay, so that was a much shorter section than I thought when I decided to do it after break, but it's done. We made it. Good job. And, yeah. So now we can actually build all of this stuff that we were just talking about. And the way that I want to do that is with blockchain from scratch. So let me just... I'll just show you what parts I want you guys to focus on, and then I'll turn you loose.